This video is going to be mostly about electron configurations and energy level diagrams with a little bit of other information. So we're going to go ahead and start off with sublevel overlap. And so we were talking about sublevels at the end of the last video, and we were talking about this is the shape of the sublevels. We've got the S as a sphere and the P orbitals as these dumbbells that are in different orientations, X, Y, and Z. And these are the ones that I want you to remember that what these shapes are. And then we've got the D's and the F's, and we're not concerned about the shapes of those. Just know that they exist. Know that for the D's, there's 5 orbitals, each with 2 electrons. And for the F's, there's 7 orbitals, each with 2 electrons. And remember, as we switch from sublevel to sublevel, from S to P to D to F, it goes up by odd numbers. So there's 1 orbital in an S, there's 3 orbitals in a P, there's 5 orbitals in a D, and there's 7 orbitals in an F. And if we were talking about G, H, or I, we continue on that same. You'd have 9, 11, and 13. All right, so these sublevels where the electrons are going to be found, they actually overlap with each other in the same way that these Russian nesting dolls, they're just one inside of each other. And so those electrons actually have the ability to pass near each other, even though they're in their set sublevels, they can pass through each other's sublevels. So what we're looking at here is this guy is beryllium, and we've got 2 electrons here and 2 electrons here, and we've got a nucleus down here. And you can see that these 2 electrons on the outside have space, but it's not just this interior part isn't cut out. They have the ability to travel through all of this inner space, going from one side to the other, not just like a shell exterior, which is why chemists don't really like to use the term shell, because it makes it out to sound like there's an area where a volume where they spend time. It's the entire section. So that whole sphere is accessible to the electrons that are in the 2s sublevel. So we can look at, I really like this graphic here. So what we have here is hydrogen. It has 1 electron, and its 1 electron is in the S sublevel. Terrific. Okay, so here's the S sublevel, and so there's 1 electron. So this is showing you how dense the electrons are in that 1 sublevel. This 1s1 thing is the next thing we're going to talk about, which is electron configurations. So here's my helium, and it's element number 2, so it has 2 electrons. And so the hydrogen and the helium, they look the same, except the helium's a little darker. What that's showing you is there's more electrons there. The electron density has gone up by a factor of 2. It's twice as dense because there's 2 instead of 1. All right, so now that I've got those 2 electrons, that's energy level 1. Energy level 1 has 1 sublevel, and the sublevel that it has is the S sublevel, and it can hold, and that S sublevel has 1 orbital inside of it, so it can hold 2 electrons. So we're finished. So I have to move on to energy level 2. So energy level 2, which is period 2 on the table, the first element I come in contact with is lithium. So when the electrons go in for lithium, the first 2 electrons have to go in energy level 1, and those 2 electrons go in, and then the third electron has to go into S2. So in energy level 2, there's an S sublevel, and here it is. So it's not very dark because it's taking up a lot more volume, and there's only 1 electron taking up all that space. But you can see that the electron can pass anywhere in here, but it can also go through this section here. All right, so if I move over to beryllium, I've got 4 electrons. So the first 2 electrons are where they always are. The first 2 electrons are always going to be in the 1s sublevel. They're going to be in the 1s sublevel because that's where they want to be. That's as close as they can possibly be. If you wanted to, the way electrons work with this is they want to have the least amount of energy. And if you were put on a merry-go-round, one that somebody's like spinning by hand, if you didn't want to hold on with a great deal of force, if you wanted it to be really easy, you'd put yourself closer to the center. That way you wouldn't be moving as fast, because the further away from the center you go, you have to be moving faster to keep up with people that are in the middle. And so the first 2 electrons will always occupy the volume of space closest to the nucleus. So we've got the beryllium, again, has its first 2 electrons in the 1s sublevel. And you can see that this area around the outside of the 1s sublevel, the 2s sublevel, is a little bit darker than it is for the lithium, and that's because there's 2 electrons here. But it's not as dark as the 1s sublevel because there's 2 electrons in here, but they're confined in a smaller amount of space, so the actual electron density is going to be much higher in this little space here than it is on the outside, because I've got 2 electrons occupying this, and I got 2 electrons occupying all of this space. And so it's a lot easier to find an electron in here because they're not running around as much. But again, the electrons can pass through each other's space. So once I've moved over to boron, element number 5, I've got 5 electrons. 2 electrons can fit in the 1s and 2 electrons can fit in the 2s, and now they're full. So I have to move on to the next sublevel. And the second energy level has 2 sublevels, and that sublevel is the p, and that p has 3 orbitals. And so you can see the y orbital, the x orbital, and the z orbital. And the z orbital is red. This one here is, and that's because that 5th electron, that's where it's located. And then the 6th electron is in another orbital in the p, 2p. And the 7th electron for nitrogen is in another orbital for the 2p. And then this one becomes more red because now I'm at oxygen and I've got 4 electrons. So I've got 2 in the center in the 1s, 2 in the 2s, and then I've got 1 in the y, 1 in the x, and I have 2 in the z. That's why it's a little darker. And now I move over to fluorine, adding another electron, and now there's 2 in the z and the x. And now I move over to neon, and I've got 10 total electrons, and you can see all of them are the same electron density because I've got 2 electrons in each one of the p orbitals, the px, py, and pz. So those electrons overlap with each other within a particular sublevel. The sublevels will overlap with each other. Okay, so these little letter number designations underneath the symbols for the elements, let's talk about electron configuration. So the electron configuration is basically like giving somebody your address. So we're telling you where all the electrons are. So for the first one, it's super easy. It's hydrogen. So what you do is you write down energy level 1, and then sublevel that's in the energy level 1 is the 1s. And there's only 1 electron to deal with. So the superscript is how many electrons are in that 1s sublevel. So if I move over to carbon, carbon has 6 electrons. So the first 2 electrons are always going to be in the 1s. The next 2 electrons are always going to be in the 2s. And then carbon has 2 more electrons to deal with. And so now we put 2 electrons in the 2p. The 2p sublevel is not full, and that's fine. But I could put more in or take some out. Either way, it doesn't really matter. But this is the configuration. So I know where the first 2 electrons are, then the next 2 electrons are, and then the final 2 electrons are. And those final 2 electrons are really what deal with the reactivity of the atom. So let's write down another electron configuration. So carbon has 6 electrons to deal with. What about nitrogen? Nitrogen is the next one over, so it has 7 electrons to deal with. Okay, so I would write 1s, 2, and so now 2 of the electrons have been accounted for. 2s2, 2 more of the electrons have been accounted for. And now I've used all 7 of my electrons. So the first 2 electrons again are in the 2s, then are the 1s, and then 2 electrons in the 2s, and then the final 3 electrons are in the 3s. So you can see that as we're doing this, if I move from carbon to nitrogen, what's happening is I've just increased the number of electrons by 1 because that's what happens. And if I go to 8 electrons, which is oxygen, 1s2, 2s2, 2p4, because that p sublevel can still hold electrons. It can hold 6 total. So then if I go to 9 electrons, that's going to be fluorine. And so then we've got 1s, 2s, 2, and then we've got the 2p5. And so then I've dealt with 9 electrons. And then if I've got 10 electrons, then we're looking at neon, 1s2, 2s2, 2p6. And I filled up my second energy level fully. My second energy level has an S sublevel and a P sublevel, and I put electrons in both of those. to max them out. So what happens if I go on to an 11th electron? 11th electron would be sodium. So Na, 1s2, 2s2, 2p6, 3s1. There we go. I've moved on to 3s1. So we just keep what we had before and add an electron until that thing fills. And then once that fills, and I move on to the next sublevel or the next energy level, depending on if the energy level has been filled. And one really cool thing about this, when we're using the periodic table, where is neon located on the table? Column number 2. Sorry, not column. Row number 2 in the P block, column number 3. So let's find that. Row number 2, P block, column number 1, 2, 3. And this is where you would find nitrogen on the periodic table. And so where would we find sodium? So I go back down here, and sodium's electron, last electron was 3s1. Okay. 3s and column number 1. And this is where you'd find sodium on the periodic table. So that's sort of like a check your work thing. If you can identify that position where the electron, where the atom actually is, and then associate it with this electron configuration, you know you've got it right. So I'll have you practice these on the homework, and then you'll find them on the quiz. Okay, so here are some electron configurations. And so the electron configurations for sulfur: 1s2, 2s2, 2p6, 3s2, 3p4. So you can go to the third row, the P block, and the fourth column over and find yourself some sulfur. So an interesting part about this is this are exactly the same. So because they're exactly the same, we can have a shortcut. We can say neon plus whatever comes after neon. So this is neon's electron configuration. Why would I do that? One, well, if we have something that's really long, maybe it takes up the whole piece of paper, so I won't want to do it that way. But more importantly, what do we know about neon? It's not reactive. So these 10 electrons here in this electron configuration are off limits. They will not chemically react. That's sort of like a base to go to. So I keep building up reactive atoms, and then I get to a spot where they're not reactive anymore. And the example that I like to use usually talks about a particular part of the Lord of the Rings. Never spell it correctly, but it's the city of Minas Tirith. So let me pull this picture, put that there. All right, so here's Minas Tirith. Yay. So what's so special about this city? It's got a wall, and then it's got another wall, and then it's got another wall, and 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 then the king. So if you want to get to the king at the top, you have to break through each one of these walls subsequently to arrive there. So you just put a bunch of troops down here and you attack everybody that comes to the wall. And if they break through this wall, then everybody backs up and they go to the next wall. So this is the way, kind of way an atom is. If I wanted to attack this, or if this was an atom, I would be able to attack the exterior stuff, but all the interior stuff is free. None of this stuff is going to be accessible. So imagine instead of you, so let's say that this wall wasn't finished yet. So let me copy this image, go over here, go to the bottom. I wonder if it'll let me drop it in here. Control V, yay. Okay, so make it a little bigger. let's say that this part of the wall didn't exist. And there's just a hole there. So the bad guys, the orcs, can just come in and walk to this part and just walk around the wall. They don't have to worry about trying to bust through this gate. They just walk around the wall. So if the orc showed up and this wall hadn't been completed, what would you do as a king? You would tell everybody to line up top, right? And you would just, all right, we're just going to forget about that wall completely. And that's the way atoms are. So as you arrive, as something arrives on an atom to have a chemical reaction, the electrons that are out there free that have not completed a wall, those are accessible. Those things can react. And once I've taken those away or added electrons to it to complete the electrons, to make a new wall, then that thing becomes unreactive. So the reason that it's a nice way to write sodium neon 3s1 is because that's the only chemically reactive electron for the sodium. The other way that you know that is if you look at sodium's oxidation state, it just says 1, which means that the sodium would give away 1 electron and turn into sodium ion. And that's the 1 electron in the 3s. It doesn't have any other options. These are, again, off limits. You can't get those electrons out of the sodium atom because they are noble gas configuration. And so those noble gas configuration means a complete wall. And so that wall is not going to be able to be broken down chemically. All right, let's go back up to where we were, which was about here. So if you're, when you're going through and you're determining how you want to fill in your electrons, you have to look on your periodic table. So the way that I think about the periodic table is I think about it being in kind of like chunks. Let's use this one here is fine. Okay, so the first chunk is this one. This orbital, that's 1s. 2 electrons can fit in that. There's 2s. 2 electrons can fit in that. Here's my 2p. 6 electrons can fit there. 2 electrons, 6 electrons, 2 electrons, 10 electrons, 6, 2, 10, 6, 2, and then it's a little harder with this periodic table. 14, 10, 6, 2, 14, and then this is an old one, so it's not showing you that it goes out to 6, or sorry, it goes out to 10 and then another 6. So when I'm going to fill in electrons, I put electrons in that, then I put them there, then I put them there, then there, then there, then there, then there, then there. So it's easy for me to think about what order. I just jump from section to section, from block to block, adding electrons until they get filled up. There's a little diagram. You'll see this in the book. You might see this if you look up electron configurations, that this tells you the order at which to fill. So first I put them in the 1s, then the 2s, then the 2p, 3s, 3p, 4s, 3d. The reason that this is kind of interesting is because I am putting electrons in my 4s before I put electrons in my 3d. So I have electrons in my 4th energy level before I put electrons in the 3rd energy level. And the reason is because the electrons in the 4th energy level's S sublevel are closer to the nucleus than the electrons in the 3rd energy level's D sublevel. Those guys are further away. So you always want to put the electrons closer to the nucleus so they have the least amount of energy. So I put them in the 4s first. And so again, I just go off the periodic table and I think about those blocks and moving from sublevel to sublevel. All right, the next thing we're going to talk about is something called the energy level diagram. This is sort of a graphical representation of the electron configuration, and it takes up more space, but I find it more useful, and I think you will too. So here's the energy level diagram for hydrogen. How do you know it's hydrogen? there's only one arrow there. Each arrow, regardless of its orientation, means one electron. So if I'm looking at something and it's got one electron, and I'm talking about atoms, then I'm talking about hydrogen. Okay. And then the next one here, that's that carbon again. So 1s2, 2s2, 2p, 2. And so there are 6 electrons. So I would know that this is carbon because I could count 1, 2, 3, 4, 5, 6 total electrons. Okay, so this is the carbon atom. All right, so if we were face to face, I would ask you 2 questions, or I would say, I need you to ask me 2 questions. There are 2 things that you should look at this and be like, what and what? Those are the 2 questions. So the first question I would expect someone to ask is, why are there arrows up and down? Why aren't they in the same orientation? All right, so electrons are charged particles. Charged particles, these are charged particles that spin. So electrons are charged and they also spin. When you have a charged particle that spins, it creates a magnetic field. So if it's spinning in this direction, the magnetic field is north on top, south on the bottom. And if it's spinning this direction, it's south on top and north on the bottom. Why is this important? Well, I need to have electrons spinning in opposite directions because these are electrons. And electrons have a negative charge. So these electrons are pushing, get away from me, pushing away from each other. Okay, well, when I go to put them in the same orbital, they have to be in there together, so they can't push each other. So if they are, if it's just the negativeness, then they would push each other out of the orbital. So that's not the only thing that's going on. The other thing that's going on is I have a north pole and a south pole. The south pole is grabbing the north pole, and the north pole is grabbing the south pole on the top. And that same situation is happening here. So pull. The top and the bottom of the electrons are pulling towards each other because their magnetic fields are attracted to each other, and the middle is pushing away. But the pull on the top and the bottom overpowers the push of the negative charges, and they hold them together. If you had, if the orientation was backwards, if this was a north and this was a south, then push, 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 push. Everything is pushing away, and those electrons could not exist in the same orbital together. So yeah, that's it. So this is called the Pauli principle. And the Pauli principle is that electrons that share the same orbital have to have opposite spin. And I know we probably want to say spin right, spin left, but the term is spin up or spin down because we're discussing the orientation of the magnetic field. Is the magnetic field up or is the magnetic field down? Okay, and then the other question I would expect you to ask me is, why are these in separate orbitals? Why didn't I just put this here? And then not worry, not put anything in there at all. So again, these this on this energy level diagram, this is energy. So as I go further up the graph, those electrons have more energy. So these 2 electrons have more energy than those electrons, and these 2 electrons have more energy than those electrons. They're further away from the center of the merry-go-round, so they're having to hold on more tightly to stay in the position that they want to be in. But this electron and this electron, same amount of energy, because again, this is on this y-axis, this is a measure of energy, and they're at the same level. Alrighty, so I realized that having electrons in the same orbital allows the electrons, if they're spinning opposite, allows the electrons to stay there. But what if they didn't have to? What if there was another spot for this electron to go to that had the same amount of energy? And that's my situation up here. So instead of putting an electron here, I'm just going to put it over here. Why? Because these electrons are still pushing away from each other. They're still negatively charged. And so as long as it doesn't take any more energy to move to a different spot, then they will move to a different spot. So if I was talking about nitrogen, the next one, the next atom or the next electron would be here. So the other way, the analogy that I like to think about this is, let's say that you were, I don't know, at a Thanksgiving or something, and there are a couple of 5-year-olds there and they're fighting, and you want to segregate them. So you could put one in one bedroom and one in another bedroom. You wouldn't put them in the same bedroom. That would be a bad idea. Not if there's no effort to it. If there's 2 bedrooms right next to each other, bling, one in one bedroom, one in the other bedroom. What if there were 3 fighting 5-year-olds? Then I could put the third in this other room. And in this case, I could put it in another orbital. So what happens if there are 4? Well, at that point, instead of moving up to the 3s, because that would be more effort, you're going to add double the one up. And it's going to be arrow is going to be pointing down because it's going to have the opposite spin. And so if I have to keep going for fluorine and then keep going for the last one for neon, then that's what I'm going to do. But I'm not going to move up to the 3s because that would be more energy and they don't want more energy. Okay, and that idea is called Hund's rule. So Hund's rule is if you're adding electrons to a sublevel that has several orbitals, put 1 electron in each orbital first before doubling up the electrons. Okay. And let's look at this energy level diagram. Okay, so this is the energy level diagram for all the atoms. If you were to count up each one of these boxes, you put 2 electrons in each, you'd end up with 118 electrons. And the biggest atom, the atom with the most electrons that we have is underneath radon, and that's element 118. So I have accounted for all 118 electrons positions as I move up. So if I was talking about something like, let's say phosphorus, and I wanted to fill in the electrons for phosphorus, I could put phosphorus has 16 total electrons. So there's 1 and 2 and 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's what sulfur would look like. It'd have 4 electrons in my 3p sublevel. You could go to row number 3 on the periodic table, go to the p block, and move over 4 spots and to the 4th column in the p block, and you would find yourself at sulfur. That's it. That's all we've got. All right, thanks.